In this lecture, let's discuss convolution and correlation in a bit more detail. First, let's look at the definition of convolution in the discrete domain. So basically what we're doing is we have two functions, f and h. F convolved with h. Yeah, of course, it's a function of m and n. That m and n are the locations of the pixels, as we have discussed earlier. Is given by sigma over L and over all n and all k, such that all k, f of k into L, f of k comma L, to h of m minus k into n minus m minus k n minus L. So basically, we have to understand what is being done here. We have a function. It has a variable k. For every location of that, we basically flip the other function h and shift it over the entire k and L. Similarly, correlation is also similar. What we have here is instead of the minus sign here, we have the plus sign. So basically, we can look at a few examples to see what exactly does it mean. This is a 2D convolution case, which is most commonly used in image processing. The simpler version is, of course, the 1D convolution case. 1D convolution, G of m is the convolution of f of the function f and h is given by sigma k is equal to minus infinity to plus infinity. Here also, it's by all k and all L, we mean it can take all values from minus infinity to plus infinity. F of m minus k, h of k, which is also same as you can actually swap the functions. It can be also f of k into h of m minus k. So I've already discussed this in the last lecture, saying that f convolution with h is same as h convolution with f. This can be proved very easily by change of variable formulation. Suppose this is how we define the convolution. Sigma k equal to minus infinity to infinity, f of m minus k into h of k. Now put k dash is equal to m minus k. Then m minus k will become k dash, and k will become m minus k dash. But this is again, yeah, of course, then the summation will be in terms of the variable k dash from minus infinity to plus infinity or plus infinity, minus infinity, or whatever. But since it's a discrete summation, just lower limit and upper limit does not have a major impact. Just summing it up. Okay. And so k dash is a dummy variable. We can always change it. It's the same as k is equal to minus infinity to plus infinity, f of k into h of m minus k. So which basically means both these convolutions, even though you interchange the functions, they are the same. And also we have to look at something, the difference between convolution and correlation with more precision. G1 of m is given by sigma over the entire k, h of k into f of m minus k, where normally f will take values 0, 1, 2, 3, etc. m minus 1, because we are dealing with images. So there are no causality. So I mean, all the signals are causal. So you don't have to treat with non-causal signals. But h, what we do is we will shift h and change values over the entire positive and negative ranges. Okay. Yeah. So f is normally it's varied between 0, 1, 2, 3, etc. to m minus 1. If it's 2D, then it will be between 0, 0, 0, 1, etc. till n minus 1, comma n minus 1. Let's take a simple case of k is equal to 2 and understand how convolution and correlation works. Let's say if k equal to 2, right? So k equal to 2 implies we have values of h which is ranging from minus k to plus k. H is equal to minus 2, h is equal to minus 1, h is equal to 0, h is equal to 1, and h is equal to 2. So let's say this, so wherever the seed of the function is, we normally indicate it with an arrow to indicate that this is where the zero of the function lies. So at h of minus 2, we have value 1, h of minus 1, we have 2, etc. H of 2, we have value 1. So this is the h function which we have. Now we have to convolve this with the function f to get the result, right? The convolved output. And let's say f is having values from 0 to m minus 1. In our case, yeah, okay. Right. So we have to find a value of a function at variable m. G1 of m is the value of the function at m. So what we have to do, k is equal to k. We know it's waiting from minus 2 to 2. K is equal to minus 2 to 2, h of k, f of m minus k. So what we need the output, h of minus 2 into f of m plus 2, h of m minus 1 into f of m plus 1, etc. H of minus 2, h of 2 into f of m minus 2. This is actually the convolution output. Similarly, if we take correlation, it will be h of minus 2 and f of m. Here it was f of m plus 2. But what we have to notice here is with h of minus 2, we had f of m plus 2. And with h of minus 1, we had h of m plus 1. So there's something like an inversion which is happening here when we are applying convolution. So here we had a function like, let's say h is something like this, and f is something like this. So when we're convolving, not just taking there is the two things which are happening. One is the function is getting inverted. So this will become something like this. Something like this. Then this will be f and this will be h. One is f will become minus f. Sorry, f of x will become f of m will become f of minus m. The second thing is, apart from that, we are actually shifting it by few values, by the value of k. Okay. So it's shifting when it's inverting, shifting, and multiplying with individual terms. That is how we do convolution. So this is what g of m is for a particular m, right? But for correlation, minus sign is coming. Minus terms are together. H of minus 2, f of m minus 2, minus 1 and minus 1, and plus 1 and f2 and m plus 2. So there's no shifting here. Sorry, there's no inversion here happening for correlation. Suppose to look at this in a more tabular form. So suppose we had values f of m minus 2, f of m minus 1, f of m plus 1, f of m plus 2. In convolution, with f of m minus 2, we are multiplying h of 2. And with f of m plus 2, we are multiplying h of m minus 2. And all the terms in between. But with correlation, with f of m minus 2, we will be multiplying h of h minus 2, the h of minus 2, and with f of m minus 1, we'll be multiplying h of minus 1, etc. f of m plus 2, multiplying h of 2. So what we understand is if h of minus m is the same as h of m, then the convolution and correlation gives exactly the same output, right? So for a symmetric function, right, convolution and correlation does not have much of a difference. So here what we've done is we've fixed f, assume that f is not changing any position, but the operations are done such that we are inverting h and sliding h. Okay. So if h is a symmetric function, which we have in most of the filters, then convolution and correlation are basically the same thing. One more thing which we have to look at is how do we deal with the boundary conditions? Boundary conditions in the sense we've already seen the indexes of images, which starts from only f of 0, f of 1, etc., f of m minus 1. But to get some terms of convolution, not all, we need to multiply it with the previous values of the function. Like we need to find g of m in some cases. We need f of minus 2, f of minus 1, etc. How do we get this? See, let's put m is equal to 0 uh, in this equation. Then to find m is equal to 0, the expression is f of minus 2 into h of 2. This is the convolution expression. H of f of minus 1 into h of 1, f of 1 into h of 0, f of 1 into h of minus 1, 2 into h of minus 2. So we know the values of h of minus 1, h of minus 2, but we don't know the values of f of minus 1 and f of minus 2 because the function f is starting from f of 0. So we have to do some kind of an interpolation, or we have to replace some kind of replication for such boundary cases. Why boundary case? Because this is where the first, if you're looking at an image, where the first term of an image start, like something like this. So here we need to know the values which are actually outside of the image, which we don't know. So we have to do some sort of an interpolation here. So the most common thing is zero pad. The values which we don't know, right? We put them as equal to 0, like f of minus 1 and f of minus 2 is put to 0. Another method is we can also replicate the values with the nearest. So f of 0 is nearest to f of minus 1 and f of minus 2. We replace them with f of 0. So mostly zero padding is being used, is being the most commonly used practice. Similar is the sort of thing which happens during the end also. If we go till g of m minus 1, at the end, we require values f of m minus 1. We need values f of m and f of m plus 1 to deal with these, the last term, right? But we don't know them. So here also we have to do some sort of a similar interpolation with either zero pad them or replicate with values of f of m minus 1. So this is how the convolution works. So we can thus find the value of the convolved output at all these indices, g of 0 being the first index, g1 of 0, and g1 of 1, etc., and g of m minus 1. So in many of this, during this course, we'll be using convolution and correlation in interchangeable, the definitions in the interchangeable way, because most of the times we'll be dealing with symmetric filters. So convolving and correlating is essentially one and the same. This is similar is the case with correlation also. So basically, they're also in there for the boundary conditions. We have to zero pad them. Okay, and this is the discussion on convolution and correlation, which is not this is not meant to be very complete. We won't be discussing too many convolution correlation cases and all, but this is just for the sake of understanding for the filters which we're using, especially linear filters. We've already seen how we can use convolution as an output, as an operation for linear shift invariant systems. If you have to find the output of a particular signal through a linear shift invariant system, we basically have to find the impulse response and convolve with the signal. So that's where we'll be using convolution correlation here. Let's end this discussion here.